Okay, hi, welcome. So my name is Jim Dowling. I'm the CEO of Logical Clocks. And in this session, we're going to talk about open source, two open source platforms. We're going to talk about ROCm, which is AMD's platform for deep learning. And we're going to talk about our platform at Logical Clocks called Hopsworks, in which we're going to talk about distributed deep learning on TensorFlow using Spark. But I'm going to start with a story. Because AMD are quite new, and I'll just put things a little bit of perspective in terms of the world of GPU computing and deep learning. And I'll start with the story of the first real monopoly of the industrial world. So the East India Company ran India for a period in the early Raj. It was the British, obviously, who ran that. And they had a monopoly over trade in the Indian subcontinent. And when you have a monopoly, you can do funny things, right? So what they decided to do was build a hedge from one side of India to the other side of India. And then they decided that we could sell a commodity, salt, at a higher price on one side than on the other side. So if you take this story and bring it to what we're talking about, which is GPUs, and if we think about GPUs, you might often word associate NVIDIA. NVIDIA have almost de facto, or have had almost a de facto monopoly on GPUs for deep learning until today, until we have ROCm, which we'll talk about later on. So what NVIDIA have done with this monopoly is they decided to segment the market. You can have some GPUs for deep learning in a data center and some GPUs that are very good for deep learning, but you're not allowed to use them in a data center. So the conclusion you can draw from this is that, well, if you have a proprietary vendor with a monopoly in a market, not very good things will happen. And that's kind of where we've been in the deep learning space to now. Now, if you come to this talk, you might be interested in the new hardware that AMD have to offer for deep learning. And I'll just give you the figures straight off. These are figures that we've measured and some others have measured. There's some references where you can see the figures came from. The NVIDIA commodity card, the 2080 Ti, which is only 11 gigabytes of memory and costs twice as much as the Radeon 7, the Vega 7 card by AMD. It's a bit faster. You can see that for FP32, floating point 32 training of ResNet, it can process 322 images per second, and the Vega 7 can process 302. And for FP16, the advantage is slightly higher. But what you get for that is you get a card which costs twice as much. It has only 11 gigabytes instead of 16 gigabytes, and you're not allowed to use it in a data center, and it's not open source. So without further ado, I'm going to hand over to Ajit from AMD, who's going to talk about the ROCm platform and what they're doing in this space. Okay.
Thank you, Jim. I'm Ajit Mathews, and I lead the machine learning software engineering team for AMD. And I'm very excited to be partnering with Logical Clocks on the Hopsworks platform for the data and AI. Our platform, which is called ROCm, is a completely open source platform, as Jim mentioned. If you look at it, the machine learning workloads are inherently parallel. And the best thing that you can get to run a inherently parallel workload is GPU. And we have a ROCm stack, which is exactly doing that acceleration of the workloads on our GPU, and also on our deep learning accelerators, right? So if it's an open source platform, it has got a collection of components like the kernel driver, has got the libraries, has got the middleware components, the frameworks that we support on top of it, and last but not the least, the tools that you need to deploy the ROCm stack, right? So like the profiler, the debugger, the tracer, etc. So the whole set of components are included as part of it. Open source is very close to our heart. Whatever we do, we upstream first. So starting Linux kernel 4.17, you have Linux kernel drivers for ROCm in the upstream. It's inboxed. We also have all our user space components. It's also open source, and for you to make it to make the developers' life easier, we have packaged everything into meta packages. You can just install it very easily by doing the ROCm install. There are different programming models that we support to cater to the different needs of the developers. So if you look at the programming model, we start with HIP. It's by the way, all these programming models, we use the same compiler backend. It's LLVM. Again, it's an open source compiler backend, and it's supported on both of the CPU and the GPU targets. The HIP is officially a language that you can use. It's part of the Clang community, and you can basically develop your ROCm applications on that, right? You can take the CUDA applications also and port it to HIP, and you can run it on our ROCm stack. We have OpenMP as the constructs. If you want to write really parallel program and offload to the GPU target, you can use OpenMP there. Python's the data scientist loves it, and we have worked with Anaconda to get the Python also on the LLVM backend compiler working on our side, and we support OpenCL 2.0. So many programming models available for the developers. It's very important when you're developing these machine learning algorithms like the RNNs, the CNNs, to have extremely optimized operations like the convolutions or softmax or the ReLU, et cetera, right? So we support different operations. We have very fine-tuned math libraries and the communication libraries. So we support FP64, we support FP32, we support mixed precisions, and other numerical formats that's going to be announced later down the line. If you look at most of these operations are GEM operations, right? This is general matrix to matrix multiplication operations, and you want to get the best performance, and we are up to 98% or greater on these GEM operations. And if you were to look at our package, you will see a lot of the libraries like the BLAST library, the FFT, the fast Fourier transform, the ROColution, the ROCprim for the parallel primitives. All of these are optimized and performant on our GPU. How about the frameworks? If you look at the frameworks, we have worked closely with Google on TensorFlow, and Jim is going to show you a demo on this. And we support multi-GPU on TensorFlow. We have optimized some of our operations for TensorFlow. We work very closely with Facebook on PyTorch, and these are available as part of the Docker containers, and the Python pip wheel that I have included in the deck, and you can download it from there. State-of-the-art machine learning training is going distributed, as you all know. And one of the things that we are very focused on is how do we support multi-GPU, right? Multi-node, multi-GPU support. We have something called as RICL, which is our communication primitive, and we support both internode and intranode. So you can do intranode GPU to GPU communication. Internode, we have support for the commodity offerings like InfiniBand, Rocky, and even Ethernet, right? So we are able to support that on our stack. And we also support MPI using the UCX. Here is a graph which basically shows almost a strong scaling using parameter server, but that's just the CPU parameter server. I'll be also talking to you about the ring-based all reduce, which is what is very prominent. This slide basically talks about the GPU acceleration and distributed training. We have worked very closely with Numba on making sure that the parallel primitives for Python are supported. Our machine learning, our machine-generated code from Numba are optimized and accelerated for our GPU platform. You can basically do a conda install, conda install -n ROCm rock tools Numba, and you'll be able to basically install it. And this lets you write parallel GPU algorithms entirely from Python, right? This is what the data scientists love. They don't want to move away from Python, and we support that natively. Container orchestration is extremely important, and we support Docker and Kubernetes to do that. We have AMD GPU plugins, which can be registered into Kubernetes containers, and you are able to address it from there, right? We support, from a distributed training perspective, we support Horovod. And also, as I said, it's all ring all reduce methodology that we use. We have the TensorFlow collective all reduce strategy and the HopsML collective all reduce strategy, which is the demo that we are going to use to run it on. With that, give back to you, Jim.
Yeah, thanks. Okay, so I'm going to talk a bit about our platform called Hopsworks. And if you're stuck on premise, this is kind of like Databricks for you. It's a UI-driven platform. It's actually a REST API, and you get data, you get batch compute, so you get Spark, and we have the world's fastest Hadoop file system, HopsFS. And then we also have support for streaming analytics with both Spark and Flink. And then we have support for deep learning, and there's some novelty in there. You may see something called a feature store. I'm not going to talk too much about that. If you're interested, there's a meetup on at 6 o'clock at Mesosphere. You can find out a bit more there. But we support the feature store is kind of the central place, the data warehouse for machine learning features. And from there, we do distributed training, as Ajit mentioned, using Spark, TensorFlow, and PyTorch. And then we do serving of models on Kubernetes. So I'm going to get an Airflow to orchestrate the whole thing. I'm going to go into a bit of details on it. But what we try to do as a company is we try to make machine learning infrastructure easy. We provide infrastructure for machine learning at scale, horizontally scalable. Many of you will have seen this diagram before. If you've worked with AI, machine learning, you'll be familiar with this. It's basically showing you a little box in the middle, which is where you train your models. This is adapted from a famous Google paper on the technical debt of machine learning. And what the point Google were trying to make here was that machine learning is more than just training models on data. You have to manage the data. You have to do a lot of feature engineering, validate your data, collect your data. You have to then manage your training. You can do hyperparameter optimization across many GPUs. You can train across many GPUs. You have to manage pipelines. And you also have to manage your serving and monitor your serving. So what we do is we provide abstractions to make these things easier to use. So we have a feature store to hide the abstraction of working with feature engineering. And then we have API support for doing the other things like distributed training, hyperparameter optimization, model deployment, and so on. So what we're doing here, what we're talking about today is how do we take what Hopsworks provides, which is the ability to write notebooks in Jupyter, run them across many GPUs using Spark and TensorFlow or PyTorch. How do we seamlessly integrate ROCm into this stack? So we already support NVIDIA CUDA, as you can imagine, and we're running on Yarn. So as Ajit said, they support Kubernetes. This is Hops Yarn, so Yarn support now for ROCm. But what we want to do is basically take the programs that you would write, run on your NVIDIA GPUs, and just run them completely unchanged on the AMD hardware and on the ROCm software. So the way we're going to do it is we do it with Yarn. And if you're familiar with Yarn, Yarn is a resource manager, similar to Kubernetes or Mesos. And the resource manager manages CPU, memory, and GPUs on servers. And each server will have a node manager to manage the resources on that server. So when we start a distributed machine learning application on Hopsworks, what we do is a container is allocated to run the application master in Yarn. So that's a driver in Spark. So our driver will start on one of the servers, on that particular, on a container on the server, I should say, and on that container we'll have ROCm installed. We'll have Conda because we provide replicate Conda environments on all of the hosts, so that it's easy to pip install libraries. I'll talk about that later. And our platform is based on certificates, not based on Kerberos. So we materialize certificates to the containers so that they can use the services using TLS. So what your driver will do is it will allocate a number of executors, and each executor will get a GPU. In this case, it'll be an AMD GPU. And the container will isolate that GPU from other processes on the same host using C groups, because that's what is used in Yarn. So C group is a minimal Docker container, as you can see it. So that C group will take the device ID of the GPU, lock it to that particular C group, and when that particular container is finished executing, it will free up the GPU, and then the resource manager can allocate it to other applications that request it. So the containers will get executors from Spark, and inside the Spark executors, you can run PyTorch or TensorFlow code. I'll show you how we do that programmatically. It requires a tiny change to your code, but it makes it, you still have to make a small modification to run your code in the cluster. So we have a distributed deep learning infrastructure in Hopsworks based around a driver running executors, and each executor will have one GPU or more. But that's not enough if you're to do hyperparameter optimization or distributed training. You really do need a distributed file system to pull it together. Because if you're going to work with TensorFlow, you're going to want to manage TensorBoard. Each executor will write TensorBoard logs. So if you imagine each executor writing to the local file system, and then you have to pull all of the TensorBoard logs from every single server, that becomes a nightmare. You could think, well, I'm going to run Kubernetes, and I'll mount NFS volumes on all of the servers, but at some point that won't work at scale. You want to get checkpoints from TensorFlow and have them in your shared distributed file system. Your training data should be available so you don't have to copy it onto all of the hosts. And the models that are saved as output, they will also be available in the file system, as well as any logs that you generate. We also use it to coordinate hyperparameter optimization as well. So let me show you a bit of code to make this a bit more concrete. And if you look at this code snippet here, and if you start at the bottom rather than starting at the bottom we have the driver code running in the main scope of this Python program. So there's a line saying runs on the driver. So underneath that code will run on the driver. So what we're doing in this example is we're doing hyperparameter optimization. We're defining a dict with a set of hyperparameters. There's a learning rate and a dropout rate. So we have 6 different combinations of hyperparameters there. And then we call experiment.gridSearch, so it's going to do grid search on those parameters. And then we have two parameters to that function grid search. One is the function train, which is defined earlier in the code. And then we have the dict, h params. So that function train will run on the executors. So if I start with 6 executors, we'll get 6 executors allocated, each one with 1 GPU. And they will all run this code, each with a different learning rate and dropout rate. So from a programming perspective, this is not a big change to make to your code. You just write your TensorFlow code or your PyTorch code or your Keras code there, and you put it inside this function. And you can keep your nested functions, so you don't have to have like one global scope inside this function. You can keep your code nice and neat, and then this will run on the cluster. So the effort for programmers to go from running on a single GPU to running on many GPUs is not that high. So if we take this example and say, well, that's hyperparameter optimization, that's weak scaling as such. What about distributed training? That's a bit harder, isn't it? It's not that much harder. We're following the same programming paradigm. We have a function called train. You can call the function anything you want. And then on the last line, we're calling experiment.collectIfAllReduce. And then you have the name of the function. So if I have, let's say, 10 or 100 GPUs, and I have 10 or 100 executors, so 1 GPU per executor, then it will run 100 instances of this train function, and they will automatically build up a ring, and they will do stochastic gradient descent, synchronous stochastic gradient descent, sharing gradients around the ring. So the effort to do this is not that high. You do have to use the estimator API in TensorFlow right now. TensorFlow people are saying for TensorFlow 2.0, they will go to Keras as well. So hopefully we'll get that in by the end of the year, that you'll be able to use Keras and not just the estimator API for this. So if we put this all together, what our platform gives you is horizontal scalability the whole way, from data ingestion to data prep, feature engineering, a feature store to manage your features, and then the experimentation and the training that I showed you, the hyperparameter optimization, which runs at scale as well. And then finally, when you want to serve your models, we'll do that at scale. So let's start at the beginning. Assume our data comes in from some external sources. Our platform typically would ingest that data in Kafka. And then from Kafka, you can select to use either Spark, but we also support Flink on the platform, and Beam and Flink. So it's not released yet, but we'll have that released by the end of Q2, hopefully. And that means basically we'll be able to support TFX, or parts of the TFX framework in our pipelines. But at the moment, you typically do your feature engineering in Spark, and you would register your features with the feature store. And from the feature store, this is where data scientists come in. They don't typically work on the left-hand side there. You would have data engineers typically doing that feature engineering code and registering those features with the feature store. The data scientists will come in and they'll basically select features from the feature store and train their models and test out new model architectures, run them, and when they're happy with them, they will deploy them. And we'll see later on, they're going to deploy them using Python notebooks rather than just normal Python programs. So currently, we support TensorFlow serving server, in this case for model serving on Kubernetes. Your models get served there, and the logs that are generated, so when predictions are made on those models being served in Kubernetes, we store the logs for those predictions back into Kafka so that we can monitor the models online using Spark Streaming or Flink. So now we've covered the entire pipeline, and you can do this today. This works today. So if you've done the pipeline, you want to automate the whole thing. We have the whole pipeline. Let's automate it, and we support Airflow to do this. So Airflow can be used to build full pipelines. But typically, because we have this feature store in the middle, we would typically have more than one pipeline. You would have a pipeline filling up or backfilling the feature store with feature data, and that might run, every day or every hour, depending on your needs. And then when you need to actually train models, you would run another pipeline starting at the feature store going to serving. So finally, we have a common metadata store for storing lineage or provenance data all the way along this. I'm not going to go into too much details here, but basically our file system will intercept all file operations, read, write, create, move, and so on. And then we turn them into, so we can infer based on the type of file. If it's a protocol buffer file and in a data set called models, well, it's a TensorFlow model. So we'll attach that label to it, and then we'll know that a TensorFlow model was created, and we'll know the application that created and the user that created it. So we store all that in Elasticsearch ultimately. So one of our goals is to make distributed deep learning as easy as doing normal deep learning. And I mentioned already that we want users to work with notebooks, and Netflix do this already. The notebooks that their data scientists develop, they run in their pipelines, and they have tooling developed for that. We've also done some tooling for supporting running notebooks in pipelines. And the way our pipelines work is that when you launch a PySpark job from your Jupyter notebook, it's using a kernel called Spark Magic, and it's going to run in our Yarn cluster. So when you're happy enough with your notebook and you think it's doing a good job on whatever part of the pipeline it's working on, you can create a job from that notebook. And that notebook, that job that can be scheduled by Airflow, that will basically take the notebook file and convert it into a Python file just as it's about to run, and then it'll run it on Yarn. So what that basically means is if you're a developer, you can create your pipeline, edit your notebook, run your pipeline, go back, edit your notebook, run your pipeline again, and it will keep running the updated versions of your notebook. When you're finally happy with your notebook and your pipeline, then you can freeze them, version them, and then start running them in production. So the process of running lots of these these jobs and notebooks, we store them as experiments. This is quite similar to MLflow that you will probably have heard of during the conference. So you're able to view your old notebooks. We store the Conda environments that are associated with the notebook run. And we also store the tensor boards that were run with your experiments. So I'm going to do a demo to show you that this is real and you can get started with it today. Let's see if anything I need to actually duplicate. Okay, so this is running over a VPN on a shaky Wi-Fi to northern Sweden, so I'm sure it'll be fine. Okay, so this is Hopsworks, and you can see that we have these things called projects over here. They're kind of like GitHub repos, and it's very easy, quick, and dirty to create a new project, so you can just go ROCm. And the project itself is like a sandbox. So when you run code inside it, you can make sure that the user can only access the data inside the project and not read data from outside it. And even if the user has access to another project, they still won't be able to read the data from that project or cross-link it. Because what we're doing is we're creating new users with certificates for every project. So that's an interesting new security model, but that's not why we're here today. So I'm going to show you the platform. So ROCm was a new project. That wasn't the one I wanted to show you. So let's look at this one. And in this project, I'll just start a Jupyter notebook just to show you what we're going to do. If you look in the bottom corner down here, you can see we've only one GPU. It's a Vega ROCm. And I'm going to ask for that GPU, and I'm going to give a driver 4 gigabytes and the executor 4 gigabytes. So what it's going to do is start a notebook. And this is starting my Jupyter notebook server. And in here, I'm going to just run MNIST, because you may be familiar with MNIST. So MNIST is the hello world of machine learning. It's used to classify handwritten digits from 0 to 10. So I'm just going to run this notebook, and then I'll explain it while it's running. So I said earlier on that you have to define a function, and this is where the executor will run. So this is a hello world for Keras on TensorFlow. And what we have down here is we have this experiment.launch, this line of code. I'll make it a little bit bigger, actually, so we can see it better. Okay, so then we have experiment.launch and the name of the function. And then after that, that will return actually the TensorBoard directory where your TensorBoard logs are run, and you can just visualize them in Hopsworks. So what we can do is we can go back to Hopsworks here. Just make this a little bit better. And we can look at so we can see down here in the corner that the GPU is now being allocated and the cluster's very busy. So this is actually running on a single machine. So you can run Hopsworks on a virtual machine on your laptop, or you can run it on a 1,000-node or 10,000-node cluster. So let's have a look at the Spark application. We've got look at the executors tab here, and we'll see that there's a driver and one executor down here. And if we look at the logs for it, I think it's probably finished at this stage. Yes, it's finished. So if we look at all of the logs, we can make this a bit bigger. We can see here that it's running ROCm system management interface here. So we can see that this is ROCm running, and we started training our model. And then at some stage, it measures this utilization with 86%, and it only took 8 seconds. So that's basically ROCm. We use ROCm, an AMD GPU, to train a model that was just normal TensorFlow code running in this Hopsworks framework. Now, we can also do distributed training with the framework. We're not restricted to just running on a single node. So this is an example I ran on a different cluster. And here we can see a tensor board that was produced at the end. And the tensor board has 6 different runs, because I ran 6 different executors in parallel with 6 different combinations of hyperparameters that you can see here. So then we can find out pretty quickly what the best combination of hyperparameters are for this particular job. And you can see in this particular cluster down in the corner, we have 22 GPUs, of which 6 are being used. It's currently very late at night in Sweden. I don't think people are up. I think they're just running them overnight. Okay, so distributed deep learning is quite straightforward, I would say, on this platform. But what about putting together, we said already that we want to put together workflows. So what I do if I want to get a Python notebook and make it a job is that I can just go in here. I can say, get me a new job. We can call it ROCm. And then I can just select the Python notebook. So for data scientists, this is pretty straightforward. They can go in and say, I'll just pick one here. There's an MNIST classifier. And I can configure and create it. And we can just pick those settings and create it. And this is a job now. It's got a name, ROCm. So what I can do is I can go to Airflow, and I can have an Airflow. Here we have an Airflow tab, and I can open my Airflow here. But I can just edit this notebook, or this Airflow DAG from the UI. So this is an Airflow DAG, in case you've never seen Airflow. And we can just change the name if we want to, of these different jobs. I have 2 jobs defined here already. And that particular DAG has an operator to run these Hopsworks jobs. So we have added a Hopsworks operator to Airflow so that it will be able to launch those jobs. So then I can open Airflow, and we can run the pipeline. And you can just press run there, and it'll run your pipeline. And then that will trigger the jobs on our Hopsworks cluster and start them running. So that was like a simple 2-stage pipeline, but you could run more pipelines than that. So we can see it started running this particular job down here, and we can then open the user interface for it to see how it's going, and that's running away there. So the last thing I guess I could show is the feature store, because I mentioned it already, and it's like the gun in the Hollywood movie. If you mention it, you have to shoot it or show it. So what the feature store is in our case, it's a Hive database. And we store metadata for the feature store in our back-end distributed database called NDB. And what a data scientist would do is they'll go to the feature store here, and they'll look at the features. They'll browse them and say, well, there's an interesting feature group here of houses for sale. Let me look at some statistics for the features. We can see some here. And let's look at some correlations between the features. And they can basically do some quick analysis of the data before they actually decide to build models. So this is basically what the starting point for them. And from there, they would go ahead and write notebooks that would, I think we have one open here. Let's have a quick look at notebook here. So they would typically have a simple notebook which will select those features. We can see this code here. It will select the features from the feature store that you want, and then you can create a training data set from there. So the really nice feature of this is that you can then decide what file format you'd like to have your training data set in. So if you're working with TensorFlow, you might say TF records, but if we wanted to work with PyTorch, I just call it NumPy, and it'll create training data with NumPy. So this reduces the friction between your team, where one group maybe want the training data in TF records, another want it in NumPy, and you agree on CSV in the end. Petastorm is also supported here. And then once you've created your training data set, you go in and train your model. We have our training data set here, and it just looks as the same as we saw before. So that's basically how we put together the pipelines on the platform, and that's the end of the demo. So just to summarize then, what we saw there was ROCm, a new open source platform for deep learning on AMD GPUs. And we saw Hopsworks, which is our platform for data and AI, machine learning. And we saw it running distributed TensorFlow on Spark. And you can try this out. So in the next version of Hopsworks, which will be released within the next few weeks, 0.10, we will include support for ROCm. You can go and buy a Vega R7 for $700 and try this out. So if you're going to ask questions, please come forward to the microphone. Thank you.
Hi, you probably mentioned this, but is Feature Store also open source?
Everything is open source that we presented. So the Hopsworks platform is fully open source, and ROCm, of course, is open source. So it's built on Hive, Apache Hive, And the backend database is called NDB or MySQL cluster, which is GPL v2.
Okay.
So it's kind of a mix of different license models.
Hi, how does the throughput compare for training? Because the one what you showed was for inference, I guess, right?
Sorry, say it again.
How's it throughput for training?
Throughput for training?
Compared between V100s and the AMD GPUs.
So this was basically the
Inference.
2080 Ti versus the Radeon 7. We don't have the public data with respect to, the V100 comparison at this point in time. But, I can say that, FP32 support, it's like almost like 30 teraflops, number one, for, our data center device, which is called MI60. It's around 30 teraflops, and it has 1 terabytes per second GPU bandwidth from a HBM point of view.
I think I could say maybe because we've played around with this, and V100s might be maybe 50, 60% faster for the FP32 workloads we've looked at for things like ResNet than the Vega, even the Vega or 7 that we've been playing around with. But the MI50 and MI60 will come out. I mean, the thing is that the commodity, I'll be honest, the commodity GPUs are very, very good in terms of throughput, not necessarily in terms of energy consumption. But this is very competitive in terms of performance.
Thank you.
Anyway, okay, thanks. Okay, I think we're out of time.
Looks like we're out of time. Yeah, if you have any questions, you are hanging around here. So.
And today is ROCm's 3rd birthday.
That's
so
right.
we can celebrate that with a
Yes.
drink. Thanks.
Thank you, folks.